An integrated circuit or monolithic integrated circuit is a set of electronic circuits on one small plate of semiconductor material, normally silicon. This can be made much smaller than a discrete circuit made from independent electronic components. ICs can be made very compact, having up to several billion transistors and other electronic components in an area the size of a fingernail. The width of each conducting line in a circuit can be made smaller and smaller as the technology advances. In 2008 it dropped below 100 nanometers, and has now been reduced to tens of nanometers. ICs were made possible by experimental discovery showing that semiconductor devices could perform the functions of vacuum tubes, and by mid-20th century technology advancements in semiconductor device fabrication, the integration of large numbers of tiny transistors into a small chip was an enormous improvement over the manual assembly of circuits using discrete electronic components. The integrated circuit's mass production capability, reliability and building block approach to circuit design ensured the rapid adoption of standardized integrated circuits in place of designs using discrete transistors. ICs have two main advantages over discrete circuits: cost and performance. Cost is low because the chips, with all their components, are printed as a unit by photolithography rather than being constructed one transistor at a time. Furthermore, packaged ICs use much less material than discrete circuits. Performance is high because the IC's components switch quickly and consume little power as a result of the small size and close proximity of the components. As of 2012, typical chip areas range from a few square millimeters to around 450 square millimeters, with up to 9 million transistors per square millimeter. Integrated circuits are used in virtually all electronic equipment today and have revolutionized the world of electronics. Computers, mobile phones, and other digital home appliances are now inextricable parts of the structure of modern societies, made possible by the low cost of integrated circuits. Terminology. An integrated circuit is defined as a circuit in which all or some of the circuit elements are inseparably associated and electrically interconnected so that it is considered to be indivisible for the purposes of construction and commerce. Circuits meeting this definition can be constructed using many different technologies, including thin-film transistor, thick-film technology, or hybrid integrated circuit. However, in general usage, integrated circuit has come to refer to single-piece circuit construction, originally known as a monolithic integrated circuit. Invention. Early developments of the integrated circuit go back to 1949, when German engineer Werner Jacobi filed a patent for an integrated circuit-like semiconductor amplifying device showing 5 transistors on the common substrate in a 3-stage amplifier arrangement. Jacobi disclosed small and cheap hearing aids as typical industrial applications of his patent. An immediate commercial use of his patent has not been reported. The idea of the integrated circuit was conceived by Geoffrey W.A. Dummer, a radar scientist working for the Royal Radar Establishment of the British Ministry of Defence. Dummer presented the idea to the public at the Symposium on Progress in Quality Electronic Components in Washington, D.C., on 7 May 1952. He gave many symposia publicly to propagate his ideas, and unsuccessfully attempted to build such a circuit in 1956. A precursor idea to the IC was to create small ceramic squares, each containing a single miniaturized component. Components could then be integrated and wired into a bidimensional or tridimensional compact grid. This idea, which seemed very promising in 1957, was proposed to the U.S. Army by Jack Kilby and led to the short-lived micromodule program. However, as the project was gaining momentum, Kilby came up with a new, revolutionary design. The IC, newly employed by Texas Instruments. Kilby recorded his initial ideas concerning the integrated circuit in July 1958. successfully demonstrating the first working integrated example on 12 September 1958. In his patent application of 6 February 1959, Kilby described his new device as a body of semiconductor material, wherein all the components of the electronic circuit are completely integrated. The first customer for the new invention was the U.S. Air Force. Kilby won the 2000 Nobel Prize in Physics for his part in the invention of the integrated circuit. His work was named an IEEE milestone in 2009, half a year after Kilby. Robert Noyce at Fairchild Semiconductor developed his own idea of an integrated circuit that solved many practical problems Kilby's had not. Noyce's design was made of silicon, whereas Kilby's chip was made of germanium. Noyce credited Kurt Lehoveck of Sprague Electric for the principle of p-n junction isolation caused by the action of a biased p-n junction as a key concept behind the IC. Fairchild Semiconductor was also home of the first silicon gate IC technology with self-aligned gates, the basis of all modern CMOS computer chips. The technology was developed by Italian physicist Federico Faggin in 1968, who later joined Intel in order to develop the very first single-chip central processing unit, for which he received the National Medal of Technology and Innovation in 2010. Generations. In the early days of simple integrated circuits, the technology's large scale limited each chip to only a few transistors, and the low degree of integration meant the design process was relatively simple. Manufacturing yields were also quite low by today's standards. As the technology progressed, millions, then billions of transistors could be placed on one chip, and good designs required thorough planning, giving rise to new design methods. SSI, MSI and LSI. The first integrated circuits contained only a few transistors. Early digital circuits containing tens of transistors provided a few logic gates, and early linear ICs such as the Plessey SL201 or the Philips TAA320 had as few as 2 transistors. The number of transistors in an integrated circuit has increased dramatically since then. The term large-scale integration was first used by IBM scientist Rolf Landauer when describing the theoretical concept. That term gave rise to the terms small-scale integration, medium-scale integration, very large-scale integration, and ultra-large-scale integration. The early integrated circuits were SSI. SSI circuits were crucial to early aerospace projects, and aerospace projects helped inspire development of the technology. Both the Minuteman missile and Apollo program needed lightweight digital computers for their inertial guidance systems. The Apollo guidance computer led and motivated the integrated circuit technology, while the Minuteman missile forced it into mass production. Government space and defense spending still accounted for 37% of the $312 million total production. The demand by the U.S. government supported the nascent integrated circuit market until costs fell enough to allow firms to penetrate the industrial and eventually the consumer markets. The average price per integrated circuit dropped from $50 in 1962 to $2.33 in 1968. Integrated circuits began to appear in consumer products by the turn of the decade, a typical application being FM intercarrier sound processing in television receivers. The first MOS chips were small-scale integrated chips for NASA satellites. The next step in the development of integrated circuits, taken in the late 1960s, introduced devices which contained hundreds of transistors on each chip, called medium-scale integration. In 1964, Frank One last demonstrated a single-chip 16-bit shift register he designed, with an incredible 120 transistors on a single chip. MSI devices were attractive economically because while they cost little more to produce than SSI devices, they allowed more complex systems to be produced using smaller circuit boards, less assembly work, and a number of other advantages. Further development, driven by the same economic factors, led to large-scale integration in the mid-1970s, with tens of thousands of transistors per chip. SSI and MSI devices often were manufactured by masks created by hand-cutting ruby lathe. An engineer would inspect and verify the completeness of each mask. LSI devices contained so many transistors, interconnecting wires, and other features that it is considered impossible for a human to check the masks or even do the original design entirely by hand. The engineer depends on computer programs and other hardware aids to do most of this work. Integrated circuits such as 1K-bit RAMs, calculator chips, and the first microprocessors that began to be manufactured in moderate quantities in the early 1970s, had under 4,000 transistors. True LSI circuits, approaching 10,000 transistors, began to be produced around 1974, for computer main memories and second-generation microprocessors. VLSI, the final step in the development process, starting in the 1980s and continuing through the present, was very large-scale integration. The development started with hundreds of thousands of transistors in the early 1980s, and continues beyond several billion transistors as of 2009. Multiple developments were required to achieve this increased density. Manufacturers moved to smaller design rules and cleaner fabrication facilities, so that they could make chips with more transistors and maintain adequate yield. The path of process improvements was summarized by the International Technology Roadmap for Semiconductors. Design tools improved enough to make it practical to finish these designs in a reasonable time. The more energy-efficient CMOS replaced NMOS and PMOS, avoiding a prohibitive increase in power consumption. In 1986, the first 1 megabit RAM chips were introduced, containing more than 1 million transistors. Microprocessor chips passed the million transistor mark in 1989 and the billion transistor mark in 2005. The trend continues largely unabated, with chips introduced in 2007 containing tens of billions of memory transistors. ULSI, WSI, SOC and 3D IC to reflect further growth of the complexity. The term ULSI, that stands for ultra-large-scale integration, was proposed for chips of more than 1 million transistors. Wafer-scale integration is a means of building very large integrated circuits that uses an entire silicon wafer to produce a single super chip. Through a combination of large size and reduced packaging, WSI could lead to dramatically reduced costs for some systems, notably massively parallel supercomputers. The name is taken from the term very large-scale integration, the current state of the art when WSI was being developed. A system on a chip is an integrated circuit in which all the components needed for a computer or other system are included on a single chip. The design of such a device can be complex and costly, and building disparate components on a single piece of silicon may compromise the efficiency of some elements. However, these drawbacks are offset by lower manufacturing and assembly costs and by a greatly reduced power budget. Because signals among the components are kept on die, much less power is required. A three-dimensional integrated circuit has 2 or more layers of active electronic components that are integrated both vertically and horizontally into a single circuit. Communication between layers uses on-die signaling, so power consumption is much lower than in equivalent separate circuits. Judicious use of short vertical wires can substantially reduce overall wire length for faster operation. Advances in integrated circuits. ICs have consistently migrated to smaller feature sizes over the years, allowing more circuitry to be packed on each chip. This increased capacity per unit area can be used to decrease cost or increase functionality. See Moore's law, which, in its modern interpretation, states that the number of transistors in an integrated circuit doubles every 2 years. In general, as the feature size shrinks, almost everything improves. The cost per transistor and the switching power consumption per transistor go down, and the speed goes up. See Dennard scaling. However, ICs with nanometer-scale devices are not without their problems, principal among which is leakage current. Although innovations in high-kappa dielectrics aim to solve these problems, since these speed and power consumption gains are apparent to the end user, there is fierce competition among the manufacturers to use finer geometries. This process, and the expected progress over the next few years, is described by the International Technology Roadmap for Semiconductors. Among the most advanced integrated circuits are the microprocessors or cores, which control everything from computers and cellular phones to digital microwave ovens. Digital memory chips and application-specific integrated circuits are examples of other families of integrated circuits that are important to the modern information society. While the cost of designing and developing a complex integrated circuit is quite high, when spread across typically millions of production units, the individual IC cost is minimized. The performance of ICs is high because the small size allows short traces, which in turn allows low-power logic to be used at fast switching speeds. In current research projects, integrated circuits are also developed for sensoric applications in medical implants or other bioelectronic devices. Special sealing techniques have to be applied in such biogenic environments to avoid corrosion or biodegradation of the exposed semiconductor materials. As one of the few materials well established in CMOS technology, titanium nitride turned out as exceptionally stable and well suited for electrode applications in medical implants. Computer-assisted design. Classification. Integrated circuits can be classified into analog, digital and mixed signal. Digital integrated circuits can contain anywhere from 1 to millions of logic gates, flip-flops, multiplexes, and other circuits in a few square millimeters. The small size of these circuits allows high speed, low power dissipation, and reduced manufacturing costs compared with board-level integration. These digital ICs, typically microprocessors, DSPs, and microcontrollers, work using binary mathematics to process 1 and 0 signals. Analog ICs, such as sensors, power management circuits, and operational amplifiers, work by processing continuous signals. They perform functions like amplification, active filtering, demodulation, and mixing. Analog ICs ease the burden on circuit designers by having expertly designed analog circuits available instead of designing a difficult analog circuit from scratch. ICs can also combine analog and digital circuits on a single chip to create functions such as A/D converters and D/A converters. Such mixed-signal circuits offer smaller size and lower cost, but must carefully account for signal interference. Modern electronic component distributors often further subcategorize the huge variety of integrated circuits now available. Digital ICs are further subcategorized as logic ICs, memory chips, interface ICs, power management ICs, and programmable devices. Analog ICs are further subcategorized as linear ICs and RF ICs. Mixed-signal integrated circuits are further subcategorized as data acquisition ICs and clock timing ICs.